casting. It's a unique process required to build batteries in TPPL technology, that thin plate pure lead. We start with a 2,000-pound sow of pure virgin lead, 99.99% purity. We're going to feed this sow as required to maintain 40,000 pounds of molten lead. Once we get that lead heated up to 750 degrees, we're going to be able to pump it up into our chill casting process. Chill casting is unique to making this type of battery. Let's go to chill casting. Chill casting. This is a fantastic process. We take molten lead, 750 degrees. We've got a drum rotating with refrigerated water going through it, so it's cold. That hot lead wants to solidify against this drum, but the speed of the drum is specifically calculated so that as the lead solidifies, we get a finished strip 1 millimeter thick. Once we have our strip, then we're able to cut it, split it, and wind it as required for the different capacity batteries that we're manufacturing. Maintaining 1 millimeter of thickness is absolutely critical to this process. We do that with a laser reader that is able to scan the thickness of the strip coming off the chill casted wheel. Then we have our 1 millimeter strip onto our reel. Once we get a completed reel, then we can send it down to perforation and begin to perforate, punch in that grid pattern that we need in order to apply our oxide. So let's go to perforation. Thin plate pure lead. We have our chill casted strip 1 millimeter thick. We need to take this strip and feed this into this high-speed perforator so that we can get a grid pattern. So this perforator is running about 1,000 strokes a minute, and it's punching in this grid pattern, and it's also splitting that feed into two finished products. So coming out of the perforator, we have our finished individual strips, run it through a cleaning process, and again, under tension. We got to keep this under tension, otherwise it gets all bent up because of this being pure virgin lead. It has no natural stifter, so it's very soft. So we feed it into our reel. We'll fill this reel up. From here, we're going to send these reels over to the pasting department. Hot air going through, and when the particles, as the nuggets break together, get small enough, then the air oxidizes the lead and then eventually blows it out of the mill. From there into a collecting chamber, and then from there it's blown up into our silo so that we have our working inventory for the pasting department. Pasting. So we have our perforated strip. We're feeding our perforated strip into our paster, and then here's the oxide. This is that oxide that came out of the oxide mill. It's been mixed with acid and water. Now we're going to apply that paste. This is where we chemically store electrical energy. We're going to put that paste onto the strip. We're going to feed it with thin pasting paper, top and bottom, so that we're going to be able to stack the plates so that they don't stick together. We feed our pasted strip with our pasting paper into a rotating cutter, and we have our finished product. Now, it's critical that the thickness of the plate be maintained. We do that by measuring the individual weight of the plate. So as you can see here on this graph, we have our band of minimum to maximum weight, and then the blue line are the actual weights of our individual plates. We're weighing every single plate, and if a plate gets out of spec, it's actually dropped down off the conveyor so that it doesn't get into our process. The thickness of this plate is absolutely critical to being able to get the plates into the container. If they're too thin, they rattle around inside the battery. If they're too thick, then we can't stuff them into the container. So this is a critical control process that's done really well by Intersys. From here, let's move on to subassembly. Plate stacking, a real unique process. We're taking our positive plates, our negative plates, and our absorbed glass mat separator. We're bringing in our negative, we feed in the pad, we bring in our positive, and what we're doing is we're stacking up the necessary quantities of positives and negatives with the pad between required for each individual battery model. From here, we're going to take this plate assembly, put it onto this conveyor, and then feed it down into our encapsulation process. This plate assembly for each of the 6 cells in a 12-volt battery is 28% larger, so we need to compress that down to get to the dimension of the Odyssey container. Once inserted, then that compressibility is maintained by the special plastic of the container, and now we're ready to cast on our inner cell lead. Notice how the inner cell connectors go up and over the cell walls, giving us the maximum amount of energy density. Of course, there are other AGM batteries on the market, including popular spiral design, or as they are sometimes called, 6-pack batteries. But they can't match the starting and reserve power of the Odysey battery. Here's why. In a spiral design battery, there is a good deal of wasted space, about 15% of the battery's volume. The Odysey battery uses every bit of space inside the case to maximize the surface area. As a result, it has 28% more cold cranking amps and up to 40% more reserve capacity than typical spiral design batteries. Coming up the ramp in this case is an Odysey Group 31 in subassembly. We have our plate assembly stuffed into the container. Our inner cell connectors have all been cast on. They're very unique, very large in overall cross-sectional area. We're going to put a weld across, bring them together. Large brass terminals that are tin plated, and we fill the complete cavity with lead, being able to transfer the maximum amount of power from inside the battery to the outside. From here, we're going to go to the high pot test, where we're going to pass 1,300 volts through each 2-volt cell assembly to assure at this point that we haven't incurred any kind of damage from this assembly procedure. So let's go to the high pot test. From the time that we started melting lead back there at Chillcast until this process, it's been almost a week of time. So we need to assure that at this point, after that sensitive sub-assembly procedure, that we've got a good battery, it's got good integrity. So this is a high voltage robotic test where we're passing 1,300 volts per 2-volt cell, doing it robotically to assure that we have no short circuits and no opens or interruptions. From here, we're going to our welding process. So let's go to welding. Welding the inner cell connectors, we use a plasma gas. Why plasma? Plasma has a very inert arc, very, very clean. Allows us to bridge our inner cell connectors and do it with no impurities. Performance, cold cranking amps. It's all about getting this chemically stored energy back out as electrical energy. We need to have large inner cell connectors that can efficiently conduct that power. The Odysey is unique. It has a connector system that goes up and over the cell wall. Traditional batteries, the plates are down lower and they punch a hole through the wall and they have this small little weld. All that power's got to go through that small weld. Here we have these massive inner cell connectors with this unique weld that maintains that cross-sectional area. So we efficiently can extract the power out of the plates and then transmit that power into these very large terminal assemblies with that brass terminal. Tin plated so there's no external type of corrosion. So from here, we're ready to actually put our cover onto the battery and begin the finishing process. So let's go down to cover assembly. Epoxy dispensing into the cover. With the polyester polycarbonate material of the Odysey battery, we need to epoxy the cover onto the container. Most manufacturers are heat sealing their cover on. We also fill these small pools with epoxy, and that unique inner cell connector that goes up and over is going to be immersed down into that pool so that we have a full epoxy bonded inner cell connector system. With our cover, we're now ready to bring the battery in, turn it upside down, and because those plates are under such high compression, our assembly doesn't fall out, and we're then going to insert the battery into the cover and then give the epoxy a chance to cure. Acid fill, a unique process. The terminal assembly's been completed. We bring the batteries in, and there is a computer that precisely measures the volume of acid that's going to be dispensed into the battery. Now that's important because these are USDOT and IATA certified batteries so that they can be shipped non-hazardous, non-spillable. So the volume of acid that is introduced into the battery has to be absorbed by the components of the battery so that it is a battery that if it were to break open, there would be no excess acid. Once the acid has been dispensed into the battery, we're ready to go into formation and electrically bring these batteries to life. So let's go to formation. Formation. This is where we electrically bring the battery to life. Our acid has been dispensed into the battery. We're now ready to electrically bring the oxide to life by passing a current through it over a prolonged period of time. That makes a chemical change inside the battery that electrically brings it to life. After formation is complete, we're going to be ready to take it down to an individual high discharge rate tester so that we test each individual battery to assure what gets shipped is a perfectly good, full specification Odyssey product. Let's go down to high rate testing. Throughout the process, it's been all about performance. This is the final quality control check to assure that the performance that was designed in and manufactured into this Odyssey battery is in fact here. We're doing a computerized test of applying a 1400 amp load, in this case on a Group 31 Odyssey, and we're monitoring the voltage under load. If this battery performs, gives voltage above a minimum level, then this battery is good to ship. And at that point, we're ready to ship this battery on.